Hey there, g'day. It's Glenn Morris from the Smart Energy Lab, and it's time for another Toolbox Tech Talk. Well, here I am again on a Sunday, and this one's coming to you as a pre-record. I can't always do it live, so sometimes it's pre-record, but that means I get to polish things a bit and fix some of my silly mistakes. But anyway, today is all about, guess what? It's Back to the Future, AS2676. Now, if you don't know what those magic numbers are all about, that's the battery standard that we used to follow for lead acid, nickel iron, nickel cadmium, and actually it said and other, which was kind of irrelevant, until the new battery standard AS/NZS 5139 came out. However, AS2676 and its companion AS3011 both got updated. So 3011 in 2019 and 2676 in 2020. So something good happened in 2020. And the reason it got updated is because it is actually all about testing and installing lead acid batteries. Well, and other vented cells too, such as nickel iron, nickel cadmium. I don't recommend you go down that path, but if you happen to have some, it provides really good guidance on how to do it. So these two standards, I've just got 2676 here because 3011's more about the installation requirements in buildings, but this is all about ventilation and testing of vented and sealed cells. So there's two parts. There's part one, which is for vented cells, i.e. flooded cells, and part two is for sealed cells. So we'll look at both of these and what the impact on those will be when you design a system. Now, one of the challenges with AS/NZS, it's not a joint standard with New Zealand, AS2676, is it's kind of written in a little awkward way, particularly when it comes to ventilation. It's not a huge standard. I'm just looking at it now. So it's got, what are we saying here? About 40 pages. Actually, it would be easy for me to see if I took my glasses off. That's way better. Yeah, it's not that bright in here with those dark glasses on, but I think it's okay. So looking at 2676, the section I want to focus on is all about ventilation and how to do the calculations. So ventilation is covered in clause 3.3. So that's what we're going to look at today, clause 3.3 and the requirements for it. So one of the things that comes up in 3.3 is how do you determine what requirements for ventilation are, whether it's a flooded cell or vented cell or a sealed cell, and also whether you're using forced ventilation or passive ventilation. So those two conditions we'll look at. So first up, ventilation is required for battery systems that have toxic or explosive gases. And there's definitely some explosive gases coming out of a lead acid battery system. Now, you might think it's only a problem with flooded cells because you can smell it. You walk into a room when they're going through absorption, or even more strongly when they're going through equalization, and there's definitely a whiff of chemicals in the air. And that's the hydrogen and oxygen being evolved and in particles, or into gas in the atmosphere. You've also got a bit of water vapor as well, and probably, some residues of that sulfuric acid. So yeah, it's a pretty pungent atmosphere if it's in high concentration, but it's also rather explosive. So it's a requirement to keep the concentration of hydrogen below 2%, because once you get up to about 4%, boom, the slightest ignition and away she goes. And if you've never experienced a hydrogen explosion, often they do them on kids' shows with a balloon with some hydrogen in it, and it makes one hell of a bang. In fact, it breaks the sound barrier, it burns so fast. So it's a very powerful explosion, and therefore it's definitely a safety issue. So you've got to keep it below 2% by volume. How do you do that? Well, let's start with a flooded cell, or what's referred to in the standard as ventilated cells. So ventilated cells are designed to actually ventilate hydrogen and oxygen under normal operation or during charging. Typically, the evolving of hydrogen and oxygen at the anode and cathode occurs in the latter stage of charging at any decent rate. So it's not till you get to about 85% state of charge that you'll really start to see those bubbles forming, and you can even hear them hissing away. It's quite noticeable. In fact, you might be able to hear a bit of rain on the roof above me. It's hissing away as well. So the keeping the hydrogen below that level requires a means of ventilation. Now, the two means that are addressed in 2676 are passive and active. Now, let's go for active first. You would think active is the best choice because you can move a lot of air quickly. And if you move a lot of air quickly, you can, with a relatively small aperture, get that hydrogen out of the danger area. But the problem with an active ventilation system is you've actually introducing a potential spark point, i.e. the motor. So it can't be on the exhaust side of the ventilation. It has to be on the inlet side. And also the requirement in AS2676 is that you have a failure alarm in case the ventilation system stops working. So that's pretty important. Otherwise, there's no point in having that active ventilation if you don't know that it's not working. So that makes it a bit more complicated than necessary, when actually it's generally very easy just to use passive ventilation. Now, passive ventilation is an aperture of an appropriate size to achieve the outcome that you want. Now, the aperture is what we're going to do today, how we calculate that aperture. So the formula in the standard, I'll just bring it back up in front of me to remind me, actually gives you a process to go through. It tells you that you need to achieve a ventilation rate by multiplying the number of cells in the system by the charging rate. And the charging rate is from all sources. So that might be solar and battery charger and inverter charger, all sources that can charge that battery, the maximum charge current. Or it can be the circuit protection on the battery system. So if you've got a 100 amp circuit breaker on the battery system, you know that you're not going to get more than 100 amps of charge current into it. So either a known maximum charge current or the protection is your charging rate in amperes. So you just multiply those together and then multiply them by a coefficient. So this is 0.006. And that the answer will be the minimum exhaust ventilation rate in litres per second. So we do that calculation, we work out how much air we have to move in terms of litres per second based on the number of cells and the maximum charge current. Then we can do the calculation for the aperture, the inlet aperture and the exhaust aperture. So both of these have to be at least this size. They can be bigger, but they have to be at least this size. And the aperture, it's a really easy one. It's 100 times the ventilation rate in square centimetres. So once you know the ventilation rate, you multiply it by 100 and that'll give you the aperture in square centimetres. Now, that seems all very simple, but you need to arrange that aperture so that you are adequately venting the gas from the enclosure or room with no gas pockets being formed, and your inlet isn't in a place where it will also act as an exhaust, i.e. it has to be below the vents, significantly below the vents of the cells. So yeah, basically an inlet at a low point, an outlet at the highest point of the minimum aperture. So let's just do this calculation. So I've got my little drawing pad here, see how this goes. We're going to calculate how to do a vented system, and this is for a, let's say it's a lead acid battery system. We've used a fairly typical system. This will be a 1000 amp hour 48 volt system, so it's a test system. So let's work out what the ventilation rate is in litres per second. So we multiply the ventilation rate equals, so ventilation rate equals 0.006. Now that's just a constant, times the number of cells. Now it's a 48 volt system. We've only got one string of cells. So being 2 volt cells, that means we've got 24 of them. And then we multiply it by the maximum charge current or the protection rating. So I'm going to say we've got 150 amp protection on the system, so that's the maximum possible charge, and that will give us a ventilation rate of 21.6 litres per second. Okay, so at this point we can go down the path of active ventilation, but we have to ensure that we can actually get that level of throughput. So 21.6 litres per second. So the ventilation system, whatever it is, will have to be rated for at least that and have an alarm in case of failure. The other option, which is the more popular one, is to use a aperture for passive ventilation. So I'll call this passive. And if you're using passive ventilation, you just need to make sure that the aperture is big enough to maintain that level of exhaust. So passive ventilation aperture. The good thing about hydrogen, by the way, is it's the lightest element in the periodic table. I mean, it's really like a party balloon on steroids. It just wants to get out of there. It wants to go up and out. It's extremely leaky too, so it doesn't take much to find its way out. So that's why the aperture is sufficient. You don't actually have to blow the hydrogen through the unit. So remember, it's 100 times the ventilation rate in square centimetres, so 100 times our ventilation rate, which was 21.6 litres per second, means that we have an aperture of 2,160 centimetres squared. Now, if you think about that in terms of area, cutting a slot, therefore that would be a slot approximately, let's call that 2.16 metres long by 100 millimetres high. So there's your slot. It's a big slot, 2 metres long, 100 millimetres high at the highest point and replicated at a lower point below, significantly below the vents to avoid any possibility that the hydrogen leaks out the inlet vent. Now, I'll talk more about the requirements of the location of equipment with respect to that vent in a minute. But what I want to do next is actually go on to a sealed lead-acid battery. So let's take a sealed lead-acid battery by contrast, and a sealed lead-acid battery has an easier job of things. So a sealed lead-acid battery, it will vent very little hydrogen. I mean, the seals aren't permanent or perfect. The seals are there actually to protect from rupture of the case due to overcharge or runaway charge. And the sealing of those cases is with a pressure valve, typically something like 6 to 30 psi. And that's to allow that gas to leak out if the pressure builds up too much. But they're not perfect seals, so there's always a small amount of leakage of hydrogen and oxygen, so you do need to have some ventilation, even with so-called sealed cells. Now, in the standard, there's a curious clause which kind of says that you've got two choices when doing the calculation for a sealed battery and calculating the charge rate. Now, the two options really are condition 1 and condition 2. Condition 1 is you're an idiot. Okay, so condition 1 is you're an idiot because it says you have no means of protecting from overcharge or overvoltage. Now, if you why I say you're an idiot, basically you're connecting a charging source and trying to manually control it and hope that you don't bust your batteries and they don't overcharge and gas wildly. So condition 1, I generally just rule out as stupid. Condition 2 is if the charger has an automatic overvoltage cutoff set at the battery manufacturer's recommended level, and therefore the charging rate is much lower. Now, the charging rate we just used was the maximum charge current for vented cells, but for sealed cells, it's actually way, way less because we know that during that absorption phase of a sealed lead-acid battery, the charge current drops away. And so the formula for that for a valve-regulated lead-acid battery with automatic, I love this word for it, automatic over-voltage protection, basically a charge controller. So over-voltage protection So you've got a charge controller connected to your battery. That could be your inverter. It could be a maximum power point tracking charge controller. So if you have this, then the ventilation requirements, so the ventilation aperture is a different formula. It's based on the amp hour rating at the C3 rating of the battery, and it's half that. So the formula is half, so multiplied by 0.5, the C3, and if you're not familiar with C ratings, it's the charge rate. So that means over 3 hours fully charging a battery. So that's pretty fast charge rate, and that will give you the maximum amount of gassing. So and then that is divided by 100 to give you your aperture. And multiplied by the number of cells, so times the number of cells, and times 100. So that 100 cancels out, actually. So that formula there can be more easily written. I'm just actually writing it out as it is in the book. But look, if you rearrange this formula, anyone who's done probably primary school maths will know that dividing by 100 and multiplying 100 cancels each other out. So therefore, the formula is simplistically written as, and using our example from before, let's just go back there. I'll put the example of, so e.g. a 1000 amp hour lead acid battery at the C3 rating. So that means it's 1000 amp hours at the C3 rating. So you've got to check that with the manufacturer, what the amp hour capacity is, and it's 48 volts. So therefore, the calculation will be 0.5, so that's half the amp hour rating, which is 1000, times the number of cells, because it's a 48 volt system, so we've got 24 cells, and times that constant or coefficient, it's constant actually, sorry, it's not a coefficient, of 0.006. And the answer will be in square centimetres, wait for it, 72 centimetres squared. Now, just think about this from before. We required 2,160 square centimetres before for a vented cell, and exactly the same capacity and voltage. The difference now is of the sealed cell, 72 square centimetres. So that's approximately a 30 mil hole saw. So approximately a 30 millimetre diameter hole is all you need. So we've done the hard work. We've calculated the ventilation requirements for both a vented cell and a valve-regulated lead-acid cell or battery system. Now we need to consider some location requirements. Now, this is out of AS 4509 Part 2. It lists the location requirements for batteries in terms of where you can't have equipment. So let's do a couple of examples. A side elevation of a battery system. So I'll draw my battery. Here's my battery here. And I'll just do the classic car battery symbol. So that's our battery system. And there is a zone where no equipment is allowed to be. And that zone here, the red zone, extends right up to the ceiling. So this is the ceiling here. It's a ceiling. And it extends 100 mils below the vents. So if my vents are here, this distance here needs to be greater than or equal to 100 millimeters. So you can't have equipment that's within the top 100 millimeters of the battery system because that's where the hydrogen's evolving. You can't have equipment above, right up to the ceiling. But it is possible to limit the sideways extent. Now, we haven't talked about the sideways extent yet, so let's just jump over to that. So the sideways extent is where we're looking in plan view from above. So I'll draw my battery system again. So here's my battery system here. And there's my, I don't know, I'm just drawing some vents on top of my battery system. Gee, that's a funny number. There we go. A bunch of vents on top of my battery system. And there's a zone around that battery system that is an exclusion zone. So that exclusion zone is 500 mils all the way around. So 500 millimeters in here, this zone here is 500 millimeters. So this is in plan view. looking down from above. So no equipment within 500 mils horizontally of the battery, and none above the battery vents, and none within the top 100 millimeters from the battery vents downwards. So those are your exclusion zones. But it is possible to limit that horizontal 500 mil exclusion zone by inserting a partition. So you might actually have, let's say, our battery system is against a wall. So here's our wall here. This is, just make it a bit thicker. There we go. That's our wall. Can't write. There we go. And we have put a partition in there. So I'm just going to get my rubber out here and rub out part of this exclusion zone, because I'm going to put a partition in. Now, for a start, the wall is a partition. That means I don't have to have an exclusion zone around the outside of my system, outside the wall, because the wall limits that exclusion zone. But I might put an internal partition in here. So there's my internal partition. And so now the exclusion zone is only the area extending to the red line. So it's significantly reduced. So that's a good thing. So it's 500 millimeters here, exclusion zone on two sides, but I've got that wall to limit the other options. Now there's another way we can do this. We can actually put the battery in its own enclosure, because these two pictures are all about a battery system in a dedicated battery room where it's ventilating into the room. And of course, there are other requirements. When you have a dedicated battery room, you need to have ability to lock it. There's some signage you need, because there's explosive gases. You've got to have a danger sign, explosive gases on the outside. Because there's liquid electrolyte in vented cells, you've got to have the green emergency sign for what to do in case of contact with skin with electrolyte. You've got to have a sign saying what the fault current is of the battery and what the battery system voltage is. You've got to have a shutdown procedure. There's really quite a few signs to go in there just on the battery itself. And you need to label the main battery isolator or isolators, and they need to be readily accessible. Now that actually comes from 5139. Now the readily accessible requirements, and also the IP23 minimum for indoor for battery isolators. So let's go to another example where we've put the battery in a box in a room. So we've got an equipment room, and the equipment room, let's just draw the equipment room. So I'll make it brownie colored. Here we go. So that's our equipment room. And within that room, we've got our battery system. The battery system is in its own dedicated enclosure. So I'll draw the dedicated enclosure, and I'm going to put a little slope on the top of that battery enclosure. So this is an elevation view of the system. So elevation. Okay. Sideways. I'm looking sideways at my battery enclosure, and inside there is my battery. So here's my batteries, all the cells. To be more specific, there's my cells. They're in here. Now we're going to need an inlet and an outlet, and the battery enclosure itself limits where hydrogen can go. So the hydrogen's not just going to leak out into the room, it's going to go wherever our vents are. So we need a vent at the high point, and we need a vent at a low point. So those two inlet and outlet points have to have the aperture as we've just calculated. So if these were sealed batteries, very small aperture. If they were flooded cells, a large aperture. And also the inlet has to be below, at least 100 mils below the vents of the battery. And it's also important to exclude equipment. Now you can't have any equipment in this zone here because it could block. So this zone here is no equipment space, and that's so that ventilation isn't compromised. You're not putting a box up against the vents. And equally on the outlet, no equipment here. That could be a spark hazard, so no equipment. Because now you don't want to discover that the equipment itself on the outside of the building could ignite the hydrogen as it's ventilating through that exhaust. So not next to instantaneous gas water heater, or Kelly-Font as they're sometimes called, not next to a inverter, etc. But once you contain that ventilation path, it does give you more flexibility about where you can install other equipment within an equipment room. So the last drawing here, last example, is actually where you put batteries and equipment all together in one enclosure. And do a little 3D drawing here. Do my best to do 3D land. Okay. So there's my all-in-one enclosure, but I'm going to put a partition in the middle, and that partition separates the battery area. So this is the battery area, and this is the electronic equipment area at the top here. All right. So now we've got a separation of the two by a basically a gas type separation. So that would have to be a solid surface. But we've got to ventilate the system now. So how do we ventilate it? So we're going to have an inlet at a low point. So we'll do, that's my inlet. And then I've got an outlet, which is at the back. So dotted line to show the outlet here. So that's my outlet. That's great. So gas will flow, through that enclosure. So you'll get through flow like this. But because the equipment enclosure also needs ventilation because it gets hot, it's an inverter or something, you've got to ensure there's no crossover of the inlet and outlet of the two compartments. So that means you've got to ensure, in this case, the inlet for the equipment would be on this side and the outlet for the equipment would be on that side. So that's the outlet for the equipment zone there. And that allows you to actually have the equipment above the battery system by managing the ventilation path of explosive gases. And it's quite practical to do that with a properly built enclosure that does have a proper seal between the battery area and the equipment area. There is, I said that was the last drawing, but there's actually one more consideration too, is to avoid gas pockets within an enclosure. So let's say you do have a battery enclosure. So here it is again, beautiful 3D drawing. All right. So that's my tall battery enclosure with cells that produce explosive gases. And so this is my inlet here. And this is my outlet at the front. So I can have the outlet at the front. That's okay. So there's my outlet there. But because it's quite a deep cabinet, it's possible to get gas pockets in there. So best practice, this is just an indicative drawing from AS NZS 4509 Part 2, is that you might have an internal partition that will reduce or force the gas towards the outlet. So this is a sloped ceiling built inside the cabinet, and that kind of pushes the gas away and back out again like this. So there you go. That's how we prevent it from forming gas pockets inside an enclosure. So there you go. That's a little guide to one of the clauses in the newly released, I'm sounding excited, AS 2676, Part 1 and Part 2, published in 2020. Now, some of you may remember that we used to have a standard called AS 4086 for battery systems, and that was in two parts, Part 1 for testing and Part 2 for installation. We actually retired both of them, but then realized that Part 1 was still valuable because it's for testing, and Part 2 being for installation was superseded by AS NZS 5139. So actually Part 1's still around. Part 1 is for testing lead-acid battery systems, and it's still valid. So there you go. These standards were last updated back in the late 90s, and were previously last updated in the late 90s, and now we've got them updated just a year or so ago for 3011 and 2676. So that's really great. Anyway, that's all for Toolbox Tech Talk today. And look, I'm hoping you're having a great Sunday or whatever day you're watching this. Please feel free to subscribe, like, all those good things. And by the way, I'll be running a course. Actually, I'm doing a 5-day course starting the 1st of March this year. It's a 4-hour sessions each day, running from in the morning at Melbourne time, and it's all online via Zoom. So via Zoom meeting. You can enroll at my courses. Go to solarquip.com. That's solarquip.com, and you can enroll in those courses. We spend 5 days talking about solar and battery design. So it takes you from woe to go. You don't have to be a professional in the area. It's there's a very low entry bar. You basically need to have a level of competence of mathematics that includes multiplication, division, subtraction, and addition. If you can get past those 4 things, I think you're good to go. A little bit of electrical knowledge wouldn't hurt, but we do cover that too. But we actually go deeper and deeper and deeper, and we cover things like the battery standards as well as the PV array standard and the inverter standard and the off-grid standard. That's why it's 5 days long. So if you're interested in learning more, sign up to one of my courses, solarquip.com. Otherwise, I'll see you next Sunday on Toolbox Tech Talk. Thanks very much, everyone. See ya.